Okay, so now let me continue talking about the derivatives. And when it comes to the derivative, as I said, it has a very particular geometric meaning. So let me first talk about the geometric meaning of derivatives. Okay, of derivatives. Sorry, derivatives. Okay. Okay. So as I mentioned, we have a tangent line. So let's write the expression of the tangent line. Let's say here, at this point A, we have a tangent line. Okay, so this is the tangent line. And now let's assume that this function f is actually differentiable at this point. So let's say f is differentiable at A, which means f prime of A, which is equal to the limit as h approaches 0 of f of A plus h minus f of A divided by h exists, right? And then this is called the derivative of f at A, and also it is the equal to the slope of the tangent line at A. Okay, and then so now if this is differentiable at A, I mean, then if you look at the graph, what can you say about the tangent line? You actually have two pieces of information. The first thing is that this line must have the slope which is equal to f prime of A, right? And then the second thing that you can say is that this tangent line must passes through the point, this point, which is A and f of A, right? And then use your high school knowledge, you can write the expression of the tangent line. So it is y equals f prime of A times x minus A plus f of A. Okay. So I think you should be comfortable with that. I mean, if it has a slope, then just write the slope here, and if it passes the point, then you just write x minus this x value and then plus the y value. So this is how you do it. So this is the expression of the tangent line. Now, as I said, if you look at the graph close enough around this point A, then you'll realize that this gives a very good approximation, right? Because I mean, this is not the graph itself is not good enough, but you can see that when this value is very close, then the difference should be very, very small, okay? So, or the error should be very small. So which means if you look at A plus H, okay, then what is the approximately value of f of A plus H? You just approximate this value f of A plus H by the value on this tangent line, right, around A, of the tangent line at A. So this is a tangent line at A, and then if h is small, then you can say that f of A plus h is approximately this value, the y value of this. But what is this value? Well, you can just write a triangle. You can just draw a triangle, and then this is h, and then the slope, which is the tangent line, is f prime of A. So which means the y increment is f prime of A times h, right? And then you know that this value is f of A. So you go from f of A going up by f prime of A times h. So which means the value here should be just f of A plus f prime of A times h, right? Or you can just plug in the value. You can just say if x is equal to A plus h, then plug in, then here the y should be f prime of A times h plus f of A, or just simply f of A plus f prime of A times h. Which means if h is small, or let's say the absolute value is less than some very small number, then f of A plus h, the value at this point of the original function, should be very close to the value at on the tangent line at this point, and then you look at the value when x equals A plus h, right? So this means f of A plus h is approximately just f of A plus f prime of A times h. And you can see that the right hand side is a linear function about h. So this is why it is called a linear approximation. So whenever a function is differentiable by the point, then we have a linear approximation around a, which means we can just say f of a plus h would be approximately f of a plus f prime of a times h. Now let me take so let's take an example. So let's say we want to find an approximate value of square root of 4.1. Then we look at the graph of square root. By the way, here if you look at the graph of square root, then here the slope of the tangent line should be infinity. Why? Because the derivative, if you take f of x to be square root of x, then f prime of x will be, as I said, 1 over 2 times square root of x. So if x approaches 0 from the right, then you will see that this will approaches to 1 over 0, which is plus infinity. Here it's to the 0 to the right. So this will be positive, so this will be positive infinity. Which means, geometrically speaking, this tangent line at this point should be just a vertical, or the limit, or the derivative is plus infinity. Okay, which means the derivative does not exist at this point, but we can say that it is infinity. Okay, so this is the correct graph by derivative, and now we want to look at 4. Let's say 4 is here. Okay. Then we want to find a value at 4.1. But we don't know what is square root of 4, but we know what is square root of 4. We don't know what is square root of 4.1, but we know the value of square root of 4, which is equal to 2, right? So this is f of 4. We want to find a value that is 4.1, but we don't know how to compute square root of 4.1, which means we will use the tangent line, okay? So if you look at the tangent line, then you realize that the derivative is 1 over 2 square root of x, and then if you evaluate this at 4, which is, so this will give you the slope of the tangent line, okay, the slope of the tangent line at the point x equals 4. So then this will be equal to 1 over 2 times square root of 4, which is 1 over 2 times 2, which is 1 over 4, which means that this has slope 1 over 4. And then you look at this point, then the value, so then by the linear approximation, f of 4.1, which is square root of 4.1, should be approximately f of 4 plus f prime of 4 times this distance, which is 0.1. And if you plug in, then the square root of 4.1 is approximately square root of 4, which is 2, plus 0.1 times f prime of 4, which is 1 over 4, okay? So you can see it's very small. And you can continue simplifying this expression, and then you can check on the calculator that it is very, very close to the real value of the square root, which means the linear approximation is actually a very good approximation. But later we'll see there are better approximations, okay, by Taylor's theorem. So here, just by the existence of the derivative, we already have a very good approximation, which is linear approximation. But later we'll see better approximations. Okay, so this is about the geometric meaning and the linear approximation. And then I want to talk about some other formulas that will be very useful, and you have to know it in calculus. So we have seen formulas like, let me say that again because it's very important. So if c is a constant, then c prime is 0, and then f plus g prime is f prime plus g prime, and then f minus g prime is f prime minus g prime. And then we have the product rule, which says fg prime is f prime g plus fg prime, while for the quotient rule, f over g prime is f prime g minus fg prime divided by g squared. Okay, and and also we know that x to the power of n, if you take the derivative, it's n times x to the power of n minus 1. So today I want to talk about some other formulas that will be very useful. The first thing is the exponential function. The exponential function has the form of e to the x, or any a to the x, okay? So where e is the constant, that is 2.71828, etc. And then this is a transcendental number, or at least a rational number. And so this is like a very useful mass constant. And then one of the reasons why it is so useful is that the derivative of e to the x is itself. So this basically says that the limit as h equal to 0 of e to the x plus h minus e to the x divided by h is going to be e to the x itself. But this is equal to, you can take out, because x is independent of h, and then this term is e to the x times e to the h, which means this is simply e to the x times the limit as h equal to 0 of e to the h minus 1 divided by h. And this should be e to the x. And because this exponential function is always positive, so you can cancel out. So in order to prove that this is correct, all you need to show is that the limit as h equal to 0 of e to the h minus 1 over h is equal to 1. And this is very important. So this basically says that when so let me put this variable into x. So as x approaches 0, e to the x minus 1 is approximately x. Is approximately x. So here, both of these are infinitesimal because e to the 0 is 1. 1 minus 1 is 0. So this will go to 0, this will also go to 0. So this is also a very important equivalence of infinitesimal. And then, as I said, you cannot prove it. You can just take it for granted. I mean, there are two ways to prove it. The first one is to define the exponential function in terms of the Taylor series or Taylor expansion. You define it in this way. Or you define the constant e in terms of a series. So this is one way. The other way is to define the constant e in terms of a limit of a sequence. So we can define e to be the limit as n goes to infinity, the limit of a sequence, which is 1 plus 1 over n to the power of n. And then in this way, you can also prove this is true. But none of these will be simple. So we'll just skip that. Okay, we'll just skip that. I mean, we can prove, but I will spend much more time on that. So we just take it for granted. So we just take this for granted that e to the x is up to a constant, up to a scalar multiplication. This is actually the only function whose derivative is itself. So what I'm saying is that if f prime is equal to f, then f of x has to be some constant c times e to the power of x. So you can prove it rigorously, but let's just skip that. Okay. This is very special, and we can say this is the only function up to a scalar multiplication, or up to a scalar multiple, such that this is true. So this shows that e is very special. Okay. Okay. But what about some other functions? What about the ln of x, which is the natural log? Okay. So this is the log e of x. Okay. What about ln of x? If you take the derivative, then this is going to be actually 1 over x. Okay. This is very important. But how do we show it? Well, you can just show it by the definition. The limit as h equals to 0 of ln of x plus h minus ln of x divided by h. This should be 1 over x. And then, so how do we show it? Well, give me 1 second. Let me see. So this difference on the numerator, I should know how to prove it, but I'm not familiar with that anymore. So this is going to be the ln of the difference of, the ln of the quotient of x plus h and this x, right? So this is going to be, so this is by some rule, right? Because ln of ab is equal to ln of a plus ln of b, and then ln of a over b is equal to ln of a minus ln of b. Okay? Which means here we're taking the ln of the difference of ln. So this will be the ln of the quotient. Okay? So then this will be ln of 1 plus h over x. And we want to divide this by h. Okay? So now let me put it in this way. So the ln of x plus h minus the ln of x divided by h is going to be 1 over h times ln of 1 plus h over x. Okay? And then you can actually write this as ln of, and again you have this rule, like ln of x to some power n is equal to, or let's say x to some power a, this is equal to a times the ln of x. Okay? Or if it's ln of x to the power of 1 over a, then this is equal to 1 over a times ln of x, right? You have all these rules. So if you use it here, this is ln of 1 plus h over x to the power of 1 over h. I mean, you can also have different ways to prove it, but maybe just spend a while to prove this is true. So you can see here, h will go to 0. But actually, you can just rewrite this as some, let's say, some y. We'll denote y by 1 over h. So then y will go to infinity, right? Then this will become the limit as of 1 plus 1 over, I mean, anyway, maybe we just skip that part. No, maybe let's continue. So here, x is fixed, and we want to find this value as h approaches 0. Okay, so maybe just let's do it. Okay, so if we do this y equals 1 over h, then this will become 1 plus 1 over x times y to the power of y as y approaches infinity, right? So we want to look at now, because h approaches 0, and then we take y to be 1 over h. So what we want is y should go to infinity. And also we are taking the ln, okay? But here, we can rewrite this 1 over xy in terms of 1 over x divided by y. And then you can actually show that instead of just having the limit as n goes to infinity, or let's say y goes to infinity, of 1 plus 1 over y to the power of y is equal to e to the y. You can actually show that for any a, you have that the limit as y goes to infinity, 1 plus a over y to the power of y is equal to, sorry, this is just e. And then here, this is actually e to the power of a, okay? So you can actually prove that this is true. So if you use it and then take the limit, because you know that the ln is continuous, so the limit, all we need to evaluate is the limit as y goes to infinity of ln of that. And then because ln is continuous, this becomes a ln of the limit of 1 plus 1 over x over y to the power of y. So then this is ln of e to the 1 over x. And then this becomes 1 over x times ln of e, which is clearly 1 over x. And we get it, okay? So maybe we can just prove, we can just play with it, and then we have all different kind of tricks that we can use. But in the end, we need to know that the derivative of ln of x is actually equal to 1 over x. Okay. Okay. And then also let me say something about the trigonometric functions. So the derivative of sine is cos, while the derivative of cos is negative sine or minus sine of x. Which means, if you want to calculate it again, so sine x double prime, which is you take the derivative twice, then it becomes the derivative of cos, which is minus sine of x, right? So first sine x prime is cos of x. And if you want to take it the third times, then it's going to be the derivative, the second derivative to the power, and then take the derivative, which is minus sine x prime, which is minus cos of x. Okay? If you take it the fourth time, then it becomes the derivative of minus cos of x, which is minus sine of x, which is sine of x. So this actually has a pattern, right? So first from sine x, and then take the derivative, it becomes cos of x, and then it becomes minus sine of x, and then it becomes minus cos of x, and then it becomes sine of x again. So which means if we denote the higher order derivative in terms of f to the bracket n, so we use this to be f prime 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 prime. So we have n, we take the derivative n times. So inductively, this is the derivative of the previous n minus 1's derivative, which means in practice, the derivative of, f, the second derivative of f will just be f prime prime. The third derivative of f would be f prime prime prime, and then the first derivative is clearly f prime, and then f to the fifth derivative should be f prime 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 prime. Okay. And if we have this notation, and then let's say if f of x is equal to sine of x, then what is f of nx for all n bigger than or equal to 0? Then it is first sine of x, and then cos of x, and then minus sine of x, and then minus cos of x, and then it repeat. So when n is congruent to 0 modulo 4, this is sine of x. And then when it's congruent to 1 modulo 4, it becomes cos of x. When it's congruent to 2 modulo 4, it becomes minus sine x. And then when n is congruent to 3 modulo 4, it becomes minus cos of x. So here, this means the remainder of modulo 4 is 0, 1, 2, 3. So for example, if n is 0, 4, 8, 12, blah, 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 then it's sine of x. For example, the fourth derivative is sine of x. The eighth derivative is sine of x. And then here, this means n is 1, 5, 9, 1, 13. This means n is 2, 6, etc. This is 3, 7, etc. So this means the remainder of n modulo 4 is this number, okay? Is either 0, 1, 2, 3. Okay, so this basically just gives a quick introduction to the higher order. And then if you want to calculate the derivative of tangent of x, then it is secant squared of x, where secant of x is 1 over cos of x, but cosecant of x is 1 over sine of x. So they're kind of different, because one might think because cotangent is paired to tangent, right? So one might think that the secant should be paired to sine, but it's wrong. Secant is the reciprocal of cos, while cosecant is the reciprocal of sine. Okay? And then we also have let's look at cotangent of x. Then its derivative is minus cosecant square of x. And if we look at secant x, then it is going to be secant x times tangent x. And then what about cosecant x? The derivative is minus cosecant x times cotangent of x. And you can just show all of these by the formulas that we have before. So you can just take that these two for granted, and then you can prove all the others. So for example, let's prove, you can prove all these, okay? So we can show that, so let's do some exercise. So let's prove that the tangent prime is secant squared. So how do we show it? Well, we just use the fact that tangent of x is equal to sine x over cos of x, right? And then we now can use the quotient rule, because we know how to compute the quotient of any. We know how to compute the derivative of any quotient. So this is f prime g minus f g prime divided by g squared. So here, this tangent x prime is sine x over cos of x, and then we take the derivative, which is the derivative of sine times cos of x minus sine of x times the derivative of cos of x divided by cosine squared of x. And then here, this is simply cos of square x. And then in the numerator, the derivative of sine is cos, right? So this becomes cos squared x. And then the derivative of cos is minus sine. So together with this minus, it becomes plus sine squared x, right? Because this is minus sine of x. And then you have minus and minus, it becomes plus. It becomes plus. And then we know that this is equal to 1, right? So this becomes 1 over cos x, or 1 over cos x squared. and then the reciprocal of cos is secant. So this is secant squared x, and then we're done. And then you can just play with it. So for example, when it's a cotangent, then you have a cos over sine, then this will become sine squared. And then here you will have all the minus, then here you have minus cos squared and minus sine squared. So that's why you have minus cosecant squared x, right? For the cotangent, that's why you have this minus sign. And similarly, you can derive the formula for secant and cosecant by using that secant is equal to 1 over cos of x, and then cosecant of x is equal to 1 over sine of x. So then you can use this rule. So the reciprocal rule, which I haven't talked about, but you can just think about this 1 as the constant function 1. So its derivative is equal to, so if you want to derive it from the quotient rule, then it's 1 prime, which is 0, times f, minus 1 times f prime. So this is 0, and then divided by f squared. So this is minus f prime over f squared. So this is called the reciprocal rule. It can be deduced from quotient rule, but also it can be used to prove the quotient rule. So the reciprocal rule says that the derivative of 1 over f is equal to minus f prime over f squared. So you can actually use the reciprocal rule together with product rule to prove the quotient rule. So let's prove the quotient rule again. The quotient rule says that the derivative of f over g is equal to f prime g minus f g prime divided by g squared. Now let's prove this by using reciprocal rule together with product rule. So the product rule says that the derivative of fg is f prime g plus fg prime. So now we can just deduce this quotient rule. So let's prove quotient rule. The derivative of f over g can be considered as f times 1 over g, right? And then take the derivatives. So then we can use the product rule. So this is f prime times 1 over g plus f times the derivative of 1 over g. So this is f prime over g plus f times minus g prime over g squared, right? So this is f prime over g minus f g prime over g squared. And then we want to multiply this by g. So this becomes g squared and then f prime g minus f g prime. Okay? So the thing is that you can, in order to prove the quotient rule, you actually can just prove the reciprocal rule. And to prove the reciprocal rule, it's much simpler than directly proving the quotient rule. So which means you can prove the product rule and the reciprocal rule and use these two rules to prove the quotient rule. And then as a result, you can deduce easily again from the quotient rule that the reciprocal rule is correct by choosing f to be the constant function 1. Okay. So this is about the reciprocal rule, the product rule, the quotient rule. Okay, that's I think that's already a lot. So